Welcome to the Explainer. Today, we're diving into a really incredible problem in modern computing. How in the world do we take these massive data-heavy AI models and shrink them down so they fit onto devices small enough to, say, power your smart lights? Well, we're going to explore a process called INT8 quantization to figure out how this shrink-ray technology actually works. And that brings us to the core dilemma we're facing today. Standard neural networks, they rely on millions of huge, highly precise numbers, which obviously requires gigabytes of RAM. But what if you want to put that AI onto a tiny microcontroller like an ESP32, which only has a few hundred kilobytes of memory? I mean, we literally can't just cram a supercomputer-sized model into a tiny chip. So how exactly do we solve this physics problem? Okay, let's dive into this. Here's our roadmap for today. First, big AI, tiny chips. Second, Float32 versus INT8 Explained. Third, the quantization formula. Fourth, inside the ESP32 brain. And finally, testing the tiny model. All right, kicking things off with section 1, big AI, tiny chips. So, to bridge that massive hardware gap on these tiny chips, the solution is creating an INT8 model. Basically, this is an AI model where the vast majority of its calculations and weights are stored as 8-bit integers. Instead of giant, continuous numbers with these crazy long decimal tails, we simply limit the numbers to a range from -128 to +127. Moving right along to section 2, Float32 versus INT8 Explained. Now, a standard AI model relies on Float32 numbers. For example, a weight stored as 0.15234 offers absolutely fantastic accuracy, but it demands 4 whole bytes of memory, which creates a huge RAM footprint. INT, on the other hand, uses only 1 byte per number. By storing approximate values instead of the exact ones, we drastically lower the memory requirement. And the real-world impact here? It's immediate. By moving from 4 bytes down to just 1 byte per number, your entire AI model becomes roughly 4 times smaller. So a 400 kilobyte model suddenly shrinks to 100 kilobytes. That is very often the difference between a model completely failing to load and running perfectly. When we weigh the exact trade-offs, INT obviously uses far less RAM. But interestingly, inference speed is often faster too. That's because doing math with simple whole numbers is just way easier for a basic processor than calculating long decimals. Now, the catch here is a slight drop in accuracy due to the approximation. But ultimately, while Float32 restricts you to really basic functions on an ESP32, INT is what actually lets you run real, deep neural networks on edge hardware. I actually want to pause on this exact quote from the source material because it is absolutely vital to understand. INT8 does not mean the AI is fake. It is the same neural network idea, but compressed. We aren't cutting out the AI's neurons or deleting its training data. No way. We are simply packing the exact same knowledge into a much tighter suitcase using those approximated integer values. Which brings us to section 3, the quantization formula. So you might be wondering, if we swap precise decimals for rough whole numbers, how does the AI still do accurate math? Well, it all comes down to a simple equation. To make INT8 work, the system stores the 8-bit integer alongside 2 powerful parameters, a scale and a 0 point. Think of these like a decoder ring, telling the microcontroller exactly how to translate that simple whole number back into a meaningful real-world value. The secret formula is real equals scale multiplied by the INT8 value minus the 0 point. Let's walk through this step by step so you can see how logical this magic actually is. Step 1. The AI identifies its stored decoder parameters for a specific layer. Let's say we have a scale of 0.1 and a 0 point of 0. Step 2. It grabs the compressed INT8 value from memory, which in this case is 25. And step 3. It plugs them right into the formula. 0.1 times 25 minus 0. Boom. The microcontroller instantly knows the exact real value is 2.5. It basically did complex decimal math, but mostly used cheap integer storage to get there. And, if you're a developer building this, you can actually verify that this compression is working just by checking your ESP32 device logs. A standard uncompressed float model is just going to show a flat scale of 0 and a 0 point of 0. mostly because it doesn't need to decode anything. But when you load an INT model, you'll see active specific numbers pop up in your logs. You might see an input scale of 0.0078125 and an input 0 point of -128. When you see those active parameters, you know for sure your quantitation shrink ray is successfully running. Okay, let's look at the hardware in Section 4, inside the ESP32 brain. When we look at the actual physical hardware where this AI lives, the software stack making the whole thing happen is built around micro-TFL Lite. Essentially, TensorFlow Lite Micro is your core AI inference engine. Micro-TFL Lite just acts as an Arduino-friendly wrapper. It's a bridge that allows developers to easily command that AI engine specifically on an ESP32 S3 microcontroller. Now, what's really interesting here is that because we're so constrained, we have to strictly manage the real estate inside this tiny chip. The actual AI model file, that's permanently stored in the chip's flash memory. But when the AI needs to think and run calculations, it uses RAM. So we carve out a specific block of RAM called the Tensor Arena to act as the AI's workbench. We really try to put this in the internal SRAM because it is literally the fastest memory available. Developers have to be super careful here too. Things like active Wi-Fi or using slower PRAM for camera images, well, those will eat right into your available resources, leaving way less room for the AI to do its thing. All right, final stretch. Section 5, testing the tiny model. To prove this all works in the real world, the source material tests a tiny AI model that was trained to solve a pretty simple mathematical equation, y equals 2x plus 1. The test environment allows the user to input any raw number from -128 to +128 over a serial connection. And before the AI processes the number, the code normalizes it by dividing the input by 100. This is super important because it exactly matches how the model was trained in the cloud. But before we even let the AI calculate the answer, the code takes some strict precautions to ensure our tiny chip doesn't just crash. It allocates a precise 20 kilobyte block of memory for that tensor arena we talked about earlier. On top of that, the code carefully tracks the system's totally available heap memory right before the AI model initializes, and then again right after. This is brilliant because it proves exactly how much RAM the INT8 model is consuming just to wake up and get ready. So, once the model is awake, the speed test begins. Step 1, the user inputs their number. Step 2, a highly precise internal timer starts ticking. Step 3, the AI executes its inference, doing the actual math to solve y equals 2x plus 1. And step 4, the timer stops. To ensure absolute accuracy in testing, the code actually loops this process 100 times in a row, calculating the average microseconds elapsed. This gives us a true, reliable measure of how incredibly fast the INT8 model really is. And the results printed to the console? They're the ultimate proof. The ESP32 spits out the AI's predicted answer right alongside the true mathematical answer, calculating both the absolute error and the percent error. Now, because we used INT8 quantization, there might be a tiny fraction of a percent error compared to a bulky float32 model, but that microsecond timer proves that the calculation happens blazingly fast. We have successfully run a real, highly efficient neural network on a tiny microchip. How cool is that? So we've learned how storing numbers as 8-bit integers shrinks a model by a factor of 4, we've decoded the math that makes those numbers usable, and we've proven it runs lightning fast on an ESP32. But the source material leaves us with a fantastic, really provocative challenge. Solving a straight line like 2x plus 1 is great, but can you apply these exact same quantization steps, training in the cloud, exporting as INT8, establishing a tensor arena, to teach a tiny microchip a highly complex polynomial curve like 3x to the 5th power minus 5x squared plus 2x plus 14. That is the true power of TinyML. Thank you so much for joining me today on this explainer, and I highly encourage you to go try writing that new model yourself.